Nikola Tesla said many years ago, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. Hello, everyone. My name is Mario Garcia-Sanz. I am Program Director at ARPA-E. And today, I am going to talk about one of the biggest energy challenges we are going to face over the next few decades. The North American power grid, with over 400 million customers, is many times referred as the world's largest machine ever built. It behaves like a living creature, controlling the voltage and the frequency with the injection of reactive and active power. Every time the load changes at any point, the generation also changes to keep the frequency constant. Typically, these frequency changes are damped and very stable. However, as we increase the renewable energy penetration, these frequency changes can oscillate more and more. This is especially important with the objective of transforming the US into a 100% clean energy economy by 2050. Eventually, if we do nothing, this trend can create unstable situations and blackouts. Over the next few minutes, we are going to analyze 5 problems that are the main reason of these undamped oscillations. The first problem is the grid inertia. In a conventional generation world, the power grid has very large inertia composed of the rotors of the large conventional generators across the grid. As the grid works, any load disturbance will find this large inertia, damping the frequency oscillation. However, as the renewable energy penetration increases, the inertia of the power grid decreases. In that situation, load disturbances will find less inertia and consequently will create more frequency oscillation. The second problem is the load sharing aspect of the power grid. Every time a frequency change happens, many power generators try to control it. If the control had integral parts in the algorithms, this would make the generators fight against each other, producing frequency oscillations. The solution we have today is a hierarchical control structure with primary, secondary, and tertiary levels for the short, medium, and long term, as we can see in the slide. The primary is based on the so-called droop control. This is a very simple control strategy without integral parts in the algorithm, something that works well in a conventional grid, but that should be revisited in a more sophisticated grid. The third problem is directly produced by the increase of renewable energy penetration. As this increases, the generation uncertainty of wind and solar systems have more significant effect in the grid. Also, due to the limitations of the existing infrastructure to connect these wind and solar farms to the rest of the grid, we are already ending up with curtailments due to overgeneration or line congestions. Finally, the intermittency of these wind and solar resources in combination with a larger and larger load can eventually demand unprecedented ramps. The fourth problem is related to weather events. As the table shows, the blackouts produced by weather events have increased over the last 2 decades. The table analyzes this problem region by region in the US, with a significant increase of blackouts in the last decade. Finally, the fifth problem describes a combination of the characteristics of the grid of the future. It is composed of a large renewable energy penetration level, perhaps 100% by 2050, a consumer-producer paradigm, new network topologies that allow bidirectional flow and open the door to a massive incorporation of electric vehicles, which probably will need to repower many cities, new microgrids across the power grid to increase resilience and reliability, distributed energy resources with control systems to reduce peak generation, and DC and AC networks and cybersecurity solutions. Putting these 5 problems together, we can easily see that we cannot go this way forever. The current situation is still damp and stable, but as the trends increase, we are going to see more and more grid oscillations, both in frequency and voltage. And eventually, at higher levels, this can result in instability and grid collapse. Before we propose new solutions for the future scenario, we should ask ourselves how we got here. A first analysis shows that the way we design the power grid is very sequential. First, we typically do a steady-state calculations and cost analysis to design the loads, generators, storage, and networks. After this, we calculate the protection systems. And finally, we look at the dynamic problem and design the control systems. This is a sequential way of thinking where each step limits the next one. And this is not enough to deal with the problems we just analyzed. As potential solutions and perhaps new ideas for future ARPA-E programs, I would like to suggest 6 key areas. First, a new control co-design philosophy for the new infrastructure. This will consider all the aspects at the same time and from the very beginning in a concurrent engineering way, and will include the dynamics and control systems. Second, a new control architecture beyond the Druck control solution, which will consider a high percentage of renewable energy penetration, low inertia, system-level situation awareness, a diverse grid with microgrids and electric vehicles, and a high level of resilience and reliability. Third, new computer tools to design the new power grid, incorporating dynamics and control design solutions. Fourth, new power electronic solutions to increase the controllability of the grid. Fifth, new sensors and big data to increase the observability of the grid. And finally, a new development of microgrids to definitely increase the grid resilience and reliability across the US. Let's rethink the grid of the future together to damp the oscillations and to transform the US into a 100% clean energy economy by 2050. If you have ideas, let's start the conversation. Thank you very much. And with that, let me introduce now our colleague, ARPA-E Fellow, Dr. Emily Yedinak.
Hello, good afternoon. My name is Emily Yedinak. Today, I want us to imagine solutions unknown as of yet, as it relates to our global plastics problem and the need for a new materials revolution. And I think to solve this grandiose problem, we're going to need all the brain power we can get. But to talk about this, I think it's instructive to go back in time. The year is 1869. You see, back in those years, billiards was a very popular sport. So popular, in fact, that there was a problem, because back then billiard balls were made specially from ivory. And because of the growing popularity of billiards, there was a real impending shortage of ivory. In other words, markets for billiard balls were growing and were realizing a biological constraint. There was simply not enough ivory to continue supplying the growing demand. To solve this problem, John Wesley Hyatt makes a new material. By treating cellulose with camphor, he obtained a material that could be used to replace the ivory in billiard balls. You could say this was the first plastic material, and indeed over the next few decades, advances in plastics would solve numerous materials challenges that naturally derived biological materials could not. Over the course of the 20th century, plastics became ubiquitous and necessary to modern-day life. No other material can match the convenience and price point that plastics offer. I mention this story because I believe this narrative can be instructive today. With rising CO2 levels in the atmosphere and more demand placed on limited resources, we are again faced with biological constraints. To see what these constraints are, let's look at the numbers. In 2015, the total energy global plastics production was equivalent to 80% of the energy consumed in global steel production, and was 70% higher than the energy used in cement production. If we look at emissions, the global emissions from plastics production was equal to 1/3 of the emissions from steel or cement. What's more, if we normalize plastics production per capita, it's been increasing. Globally, this trend has been rising at a near exponential rate. And to understand the implications of these trends, I need to mention the elephant in the room. You see, most of the solutions that have been proposed, besides burning the plastics outright for energy, can be grouped into 2 categories: bio-derived polymers and enhanced recycling processes. Recycling will not be enough because of our growing plastics demand, and bio-based polymers may be limited by a significant biological constraint. To illustrate this biological constraint, let's take the US as an example. Of the total domestic supply of sustainable biomass available in the year 2040, approximately half will be ag residues and energy crops. Excluding energy crops, a small fraction of ag residues are left, with about half of that constituting corn stover. I highlight corn stover because this is one of the most popular feedstocks proposed for bio-based polymers. We would have to divert nearly all of the corn stover to resin production if we are to convert to 100% bio-derived polymers, posing a significant strain on biomass supply chains and precluding any alternative uses for this biomass. Furthermore, the land intensity for US biopolymer production means that we'd need the equivalent of approximately 25% of our agricultural land to substitute for fossil fuel-based resins. If we look globally, models from the University of California, Santa Barbara suggest that recycling and bio-based polymers will not be sufficient. Under the base case scenario where plastics production increases year over year and the energy mix stays the same, greenhouse gas emissions are expected to increase, even with substituting with bio-based feedstocks, shown by the yellow and the green curves, or recycling all plastics, noted by the bottom edge of all of these curves. Only under a scenario where the plastics demand is reduced by half and the energy mix decarbonized by 2050, in addition to recycling and bio-based polymers, can life cycle greenhouse gas emissions remain steady or decrease by the year 2050. This is an incredibly aggressive scenario that requires significant coordination among many industries. So, what's next? Though we will still need recycling and bio-based polymers, I hope that I've demonstrated to this audience that these solutions are not a cure-all. We'll still need to replace plastics demand by at least half over the next 3 decades. So the question now is, how are we going to do this? In some cases, it may require completely redefining the problem. One scenario where plastics have had an overall positive impact is in food packaging. Plastics extend the shelf life of produce and meats and divert food that would otherwise go to landfills, where they will likely contribute to methane emissions. However, plastic food packaging requires multiple layers of several different types of polymers, such that it's impossible to recycle these plastics effectively. But what do we really need this packaging for? We need it to prevent bacteria from growing on our meats, and we need it to retain moisture in our produce. If we redefine the scope of the problem in this way, can we design a super polymer, or a single type of polymer that performs all the functions that several polymers do in today's modern packaging, so that the recyclability of this packaging is maximized? Can we look for edible packaging alternatives, completely negating end-of-life problems? Or perhaps in the case of crops, can we genetically modify them so that the skins prevent moisture loss, thus extending their shelf life? Redefining the problem to the basic requirements helps us re-envision alternatives to plastics for some use cases, but may not be sufficient to address all plastics uses. In some cases, we may need to invent an entirely new class of materials. And here I provide as an example, nanocellulose, which has many of the same properties as plastics. However, nanocellulose is still manufactured at relatively small scales, is too expensive relative to fossil fuel-based plastics, and is sourced only from bio-based materials production. The next materials revolution may very well require low energy, low cost production of synthetic nanocellulose, a process which could leverage many of the same bioreactors that are currently being explored for technologies like lab-grown meat. So I want to bring us back to the beginning. One of the earliest plastics alternatives was discovered because there was a biological limit imposed on the material supply chain. And today we are once again hitting a biological limit. So my question is, what will be this century's materials revolution? Thank you. And now I'd like to introduce the next fast pitch from my colleague, Dr. Phil Kim.
I have good news for everyone. My pitch involves a virtual excursion to the zoo. We'll learn how these creatures survive in extreme heat or cold and see what we could potentially do to save energy inspired by nature. My name is Philseok Kim. I'm a program director at ARPA-E, and I'd like to talk about making our buildings adaptive. This is the DOE headquarters in Washington, DC. Commercial buildings like this and our houses altogether in the US spend 21.3 quads of energy every year. The building sector uses about 75% of total electricity generated and emits over 1.8 gigatons of CO2 each year. About half of that energy is used for heating and cooling the space and making hot water. which corresponds to well over 11 quads of energy each year. Is there anything we could do to save this enormous amount of energy we are using for our buildings? We make our buildings by putting up what we call the envelopes or shells, such as the roofs, walls, facade, windows, doors, and the floor. We typically try to isolate the space inside of buildings from the outdoor environment because it can be too hot or too cold. Then we turn on the heaters or AC to control the temperature inside of the buildings at our desired comfort level. This is the traditional concept for how buildings work, and it is an energy-intensive approach, often requiring oversized HVAC equipment. We have been making our building skins as insulating as possible with minimum possible leaks. To do so, we have to put very thick insulating materials to reach the required R values for different climates that often add more cost. But why are the building skins static, only providing insulation, while the outdoor is providing free heat and cold? I live in Boston, and even on a cold winter day, the sunny side of the wall is receiving more than enough energy to heat my entire house. Is there any way we could make our buildings work with nature to utilize this free energy? If we can do so, we can save a lot of energy, downsize the HVAC equipment, and reduce emissions. Recently, there have been new buildings with what is called kinetic facade. It's shown in this movie, but this is not the type of solution I'm looking for, as they still require external power to run these actuators, even though they are dynamically changing building skins. I think we need some new ideas and inspirations here. How does nature handle it? Let's go to the zoo to take a look. What color is the fur of a polar bear? You probably think it is white, but it is not white. Their long hairs are actually translucent and hollow fibers that trap more air in between and within themselves to provide insulation. Their skin is black to absorb more sunlight to stay warm. Since their fur scatters the visible light, they appear white in the snow to disguise themselves from their prey. What a creature, isn't it? However, their skin is designed to survive only in an extremely cold Arctic environment, so I wouldn't call it fully adaptive yet. At least, the polar bears are giving us an example of achieving desired aesthetics, which is an important function that any building skins must have. Addax is an antelope originally found in the Saharan desert. This critically endangered species has evolved to survive in sizzling heat by changing its coat to a highly reflective snow white in summer and brownish coat to match with the sand in other seasons. As a result, their coat is effectively regulating the seasonal solar reflective index. They achieve it by molting, so it's adaptive, but perhaps not so applicable to the building skins. Blue jays fluff up their feathers in the cold to trap more air for insulation, and we can view it as if they have a variable thermal register built in their skin. This is truly an adaptive and reversible change, and they do it by a very simple trick. In fact, we humans have a similar but vestigial feature that used to help us stay warm in the distant past. When we feel cold, we get the goosebumps, and it happens by contracting a tiny muscle attached to the hair. Again, this is a reversible and adaptive function from a simple design. Another example of adaptive skin can be found in bearded dragon lizards. This ectothermic creature regulates its body temperature by reversibly changing its skin color, and they do so by controlling the dispersion and aggregation of melanin within the dermal cells. They can do this within seconds to minutes in response to the temperature or light intensity or pre-programmed in their circadian cycle. What if we can utilize simple principles like this to make our building skins more adaptive and effectively reduce energy consumption? As a matter of fact, ARPA-E has funded a very close idea that is called adaptive thermal-responsive textile, albeit for a different application. This fabric assembly of bimorphs lies flat when it is warm or hot, but it expands and traps air to provide insulation, when the temperature falls below the transition temperature. It is completely reversible and no power is needed. A simple idea, a brilliant new function. So here's what I'm looking for. Can we redesign our building shells to be adaptive? What if we have a roof that changes its radiative profile in response to temperature or light, just like the bearded dragons? What if we have a wall that regulates its R value in response to temperature, just like the blue jays, such that we have a thermal register or a diode-like function? How about windows that regulate the luminance in response to light intensity? By the way, to make it feasible for buildings, your idea must be scalable to at least 10 square feet and at cost parity to the best performing state-of-the-art commercial product. If you have ideas, let's talk. Now, let me turn it over to my colleague, Program Director, Dr. Bob Ledoux.
Thank you, Phil. Today, I would like to talk to you about beyond binary computing, exploring quantum computing solutions for energy's toughest problems. Specifically, let's discuss the use of quantum computers to perform quantum chemistry simulations. This, by the way, is one of the original motivations for quantum computing. So what could, and I hope will, you do with a tool that rapidly and accurately simulates any chemical reaction? Could you find an economical room temperature superconductor for low loss power transmission, or identify and simulate complex catalytic reactions to accelerate innovations in carbon capture, or identify and develop new fault-tolerant advanced reactor fuels and ultra-durable waste forms? So why can't we do this at the present? So it's not due to the fundamental physics, because by 1926, all the fundamental physics, the non-relativistic Schrodinger equation, and Pauli exclusion principle were known. The issue is that a complete solution to the Schrodinger equation scales exponentially with the number of electrons. And therefore, complete solutions are only possible for the smallest systems, and consequently, complex systems, we need to use significant approximations, and they may still be computationally prohibitive. So how do we make progress? Well, before we talk about quantum computers' approach to this problem, let's discuss this exponential scaling. So for an example of exponential scaling, sometimes referred to as the curse of dimensionality, let's consider a computational problem which scales exponentially. It scales like the number of calculations, scales like 2 to the n. And let's do that on our laptop. Okay, so for a problem size of 25, that calculation takes a 50th of a second, the time for a hummingbird to beat its wings once. Now let's double that problem size to 50. Now that calculation takes a week. And if we double that once more for a problem size of 100, that calculation takes longer than the age of the universe. Hence, now we get the curse of dimensionality. So can quantum computers help us get around this curse? And if so, how do they do it? Or could they do it? So let's discuss computing, but let's start with classical computing first. So in classical computing, the fundamental unit of information is a bit. It only takes on 2 values, 0 or 1. And then these bits are manipulated in transistor gates, and we have software to run programs on them. And in principle, a classical computer can simulate any physical system, but of course we see the limitations of exponential scaling. Now, a quantum computer is quite different. Its fundamental unit of information is a qubit. And a qubit is itself a 2-state quantum system. And if you put those 2 states into superposition, you can actually represent all the points on a unit sphere. So a lot more information basically just in 1 qubit. And quantum gates have been developed to manipulate qubits, and there's quantum software being developed. So in principle, we do have quantum computers. So where do we stand in terms of where they'll get us? Well, the very first thing to understand is that n perfect qubits can encode 2 to the n pieces of information with tremendous computational parallelism. Hence, quantum computers can, in principle, break the curse of dimensionality and potentially revolutionize quantum chemistry simulations. So that's great promise. And this is the basis for it. Now, how far are we from realizing this promise? Well, present quantum computers, sort of the state of the art, is about 50 qubits, and an example of quantum supremacy, a calculation that cannot be realized with a classical computer, has been realized in a simple simulation. Now, this plot wants to illustrate the fact that the error rate is quite high for a current state-of-the-art qubits. That is, they're relatively noisy. So this high error rate is shown in this plot. Now, quantum error correction algorithms have been developed, but the price you pay for that correction presently is that you need 100 to 1,000 physical qubits to represent one logical qubit. Still, a lot of progress is being made, hence the call to action. So what is the path forward for quantum simulations? Well, great progress is already being made, particularly in adapting and optimizing quantum chemistry calculations to quantum computers. Now, simulations have already been performed for simple chemical systems, and algorithms to harness the full power for quantum chemistry simulations are rapidly being developed. So we are at the threshold of a very important era called the noisy intermediate scale quantum computing era, and progress should rapidly be made in simulations for more and more complex chemical systems during this period. So I think that I will propose a call to action for the energy community. First, we need to identify and prioritize the near-term high-impact applications in the energy sector, where quantum calculations could significantly accelerate innovations. Secondly, we need to bring our resources to bear on leveraging this new tool. We must understand and guide this emerging field and develop applied research programs for the energy sector. And we also need a seat at the table to the larger quantum computing community, and we need to engage them to develop a long-range plan for quantum supremacy in the energy sector for applications that are very important to us. So let me thank you for your attention. I welcome any questions and comments. Hope we have a lively discussion. And I'd like to leave you with an inspirational quote from Eugene Wigner, a famous mathematician and physicist. He said, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve." And let's hope our good fortune in this regard continues. And now I'd like to introduce my esteemed colleague, Dr. David Tu, ARPA-E Program Director. David?
Good afternoon. My name is David Tu, and I'm a Program Director at ARPA-E. Today, I would like to speak with you about one of our most difficult decarbonization challenges, transportation energy storage. At the same time, I would like to introduce you to potential solution approaches that leverage the transformational potential of artificial intelligence to automate the process of invention. Maritime rail and aviation are significant warming drivers and are responsible for roughly 5% of anthropogenic CO2 emissions. Furthermore, these modes of transportation are expected to grow in importance over the coming decades. And aviation in particular, through its emissions at high altitude, has an outsized impact on global warming, even beyond its carbon dioxide emissions. Contrails associated with the condensation of water vapor exhausted from aircraft engines may actually be the most significant from a warming perspective. ARPA-E is already making investments to reduce the warming impact of aviation through its reach and descent programs. These efforts are focused on increasing the efficiency with which carbon neutral liquid fuels are converted to useful work. However, the source of the fuels is still to be determined. But for starters, over the past 2 decades, drop-in replacement synthetic aviation fuels derived from natural gas and biological sources have been developed and evaluated in commercial operation. However, their current market share is extremely small. In addition to the drop-in synthetic fuels, several additional candidates are being considered: hydrogen, ethanol, ammonia, and methane. However, none of these fuels offer the stored gravimetric and volumetric basis heating values of jet fuel. Hence, unless these alternative fuels offer unique characteristics that can be leveraged to produce thrust at differentiated efficiency levels, aircraft that use them will simply not perform as well as those using synthetic jet fuel. Let's talk about scale for a moment. In 2019, on an energy basis, the US consumed 0.7 petawatt hours of jet fuel, which represents roughly 2% or 20% of worldwide consumption. For comparison's sake, Americans consumed only 1/2 petawatt hour of food and 4 petawatt hours of electricity in 2020. Additionally, only 1.5 petawatt hours of electricity generation was from carbon-free sources. If we are to synthesize impactful quantities of transportation fuel, significant investments in either carbon-free electric generation or agricultural production capacities will indeed be required. I'd like to speak for a moment about 2 potential carbon-neutral liquid fuel production options to give you a sense of the scale of the problem. One option is to use renewable electricity to capture carbon dioxide, then electrolyze it with water to produce a mixture of CO and hydrogen that could then be converted to storable hydrocarbon fuel via the Fischer-Tropsch process. In a very approximate and very optimistic scenario, if we were to produce 1 petawatt hour of synthetic jet fuel, roughly what we might need in 2025, we will require more than 2 petawatt hours of renewable electricity to run the blowers required to capture CO2 from air, to electrolyze that CO2 with water to produce syngas, and to compress the syngas to tens of bar for the Fischer-Tropsch process. In order to meet this additional electric demand, we would need to build a carbon neutral electric generation capacity that is roughly equivalent to our current carbon neutral generation capacity solely for the purpose of producing aviation fuel. However, this electric demand would be substantially reduced via the avoidance of electrolysis by the utilization of already reduced carbon in the form of biomass. However, if our 1 petawatt hour of jet fuel, for example, were derived from corn stover, we would need to harvest stover from a land area that is roughly the size of California. As a reminder, once we have produced our jet fuel, it is loaded onto our aircraft where it's converted to thrust energy solely for the purpose of transporting people and goods, which does make this Star Trek fan wonder if I'm actually focused on the right problem. But more seriously, the transportation fuels problem is extremely complex from both market and technology standpoints. Its scale is immense, and our quality of life demands an economically attractive solution. We may indeed need help. This help may come in the form of new design tools that leverage the transformational power of artificial intelligence, and perhaps even from some of the tools that are already being developed within the Differentiate program at ARPA-E. This program has been underway for roughly a year, and here I have tried to summarize the efforts of our 23 hardworking teams. Roughly speaking, we are developing ML-based surrogate models that enable the instantaneous and high-fidelity prediction of design performance from designs. These models are in the form of deep neural networks or Gaussian processes that are trained with data that is sourced from either numerical simulations or actual physical experiments. These ultra-fast surrogate models are then being used to train reinforcement learning-based optimizers or generative models. Reinforcement learning, as you may have heard, is the machine learning approach that has been able to master many popular games such as Go, Atari, and chess, and to play them with superhuman performance. Within Differentiate, we're training our RL-based algorithms to play energy technology-related games, including the design of circuits, thermodynamic systems, and materials. These methods are showing significant promise, and that they do indeed seem to be able to learn how to optimize designs. Also, we are using our surrogate models to train generative models that are capable of instantaneously generating actual designs from requirements without any iteration. These generative models, when combined with additive manufacturing, offer the promise of low-cost, high-performing custom designs in a broad range of applications. For illustrative purposes, 3 quick examples of fuel production-related ML-enhanced design capabilities that we're actually developing within Differentiate are provided on this slide. First, Professor Jianlin Cheng from the University of Missouri is developing the ability to predict the quaternary structure of proteins, a capability that he ultimately hopes to leverage in the development of actually better algae for fuel production purposes. Second, Professor Rafa Gomez Bombarelli at MIT is developing the ability to execute the inverse design of oxygen reduction or evolution catalyst for a range of fuel production or consumption applications. Third, Professor Zach Ulysses at Carnegie Mellon is developing the ability to predict the actual structure of catalysts under their reaction conditions, a capability that he hopes to leverage to design cold catalysts that transform into their optimal structure when exposed to reactants at the appropriate pressure and temperature. We have many more exciting projects within the program. The above 3 were simply the most fuel production related at face value. In sum, the decarbonization of long distance transportation is one of our most challenging climate related problems due to its scale, as well as the importance of size, weight, cost, and safety. The ML tools being developed within Differentiate may indeed be useful tools for engineers trying to develop better fuels. Please reach out if you have fuels or tools ideas. Thank you very much for your time and attention. Look forward to answering your questions.
Thank you, Dave, and thank you, everyone. So we have about 20 minutes, for questions and answers. And so we have now, the 5 speakers, so for this question. So as you can see here in the right-hand side, we have a number of questions that are, so let me see if I can see. Okay, so let's start with Emily. There is a question for you. One solution people are looking is the waste to energy and converting plastics to fuels. What is your view on this potential solution?
Yes, thank you for the question. I did briefly mention it in my talk, but I didn't go into detail. I learned a lot about plastics over the last 2 years, and the first lesson that I learned about plastics is that plastics are not the problem, it's a waste management problem, and that's specifically regards to the proliferation of plastics in the environment. The second thing that I learned is that plastics are an incredibly long-lived, relatively speaking, carbon sink. So when my gut reaction when people or when folks, propose to convert plastic to fuels is kind of, well, you're turning a carbon sink that would have lasted several hundred years and you're releasing all the carbon in the atmosphere. So although you are trying to solve one problem, which is the plastics in the environment, you are exacerbating another problem, which is carbon emissions. So my gut reaction to that question is I'm personally not a fan, although I do recognize that there are some merits in, incentivizing collecting plastic better.
Thank you, Emily. There is a question for Bob. What areas of quantum computing outside of quantum chemistry may be of interest to ARPA-E?
Well, that's obviously a very fundamental and important question. So I focused on ones which I believe quantum chemistry, which is, I think, clearer to understand that the advantages of a quantum computer, because it is a quantum system, naturally derive. So I think anything to do with a physical thing. So I'll give you another example in ARPA-E, fusion. So in fusion, it's very difficult to simulate a full all of the dynamics of the interaction because it's just too hard to scale it. So there may be an example where you could do a full quantum mechanical calculation or semi-classical and get rid of the problem of exponential scaling problem. And I'll give one more, Mario, for you. I mean, as the heterogeneous grid grows, there are so many variables in it that if we try to take a traditional computer control approach to it, it may just not be even close to real-time control. Again, it's not a natural quantum system that you're simulating, but there's been a lot of work in optimization algorithms with quantum algorithms. So maybe that's another area. So we'll see what goes with this. Many other ones project, but I think those are a couple examples from this particular session.
Thank you, Bob. And there is a question for me here. It's saying, do you think that the oscillation should be addressed on the energy supply side, or it could be also handled at the demand side, or both? Well, I think this is probably a question about two aspects. The first one is the control authority. So control authority, as you know, is that the potential that you have to have some effect in the system. So when we are talking about the loads controlling the frequency, if these loads are very small, we have to do things in a way that when you add up many loads, so this aggregated big number, we have some control authority with the system. But perhaps the other aspect that is even more important is this aspect of the load sharing problem. So we have to control frequency. Frequency is a global variable, opposite to voltage, that is a local variable, right? So frequency is the same all over the grid. And then we have many power systems, many generators trying to control this particular frequency. And if we do things in a bad way, with integral parts in the controllers, we can end up having, these generators fighting each other. So if you put in top of that also, the loads, trying to control frequency. So the answer is, well, we can do that, but we have to do that in a way that we develop a controller strategy that is able to aggregate all this input in a way that we don't have loads and generators fighting each other, in order to control frequency. So the answer, quickly is yes. I think that we should do that with the generators and the loads, but we have to find a way to develop a controller strategy that is able, to open, all these possibilities, to coordinate, all these aspects, controlling the frequency. And by the way, with the less amount of communication as possible, because this is, for another question probably, but I think that's my opinion with that. Phil, do you think that metamaterials will play an important role in designing building materials with tailored thermal properties?
Great question. Actually, I'm really glad that people are really thinking about it. And the first thing came up was a metamaterial. I haven't really thought about it. But I do think that if it can be engineered such that it can have like thermal or infrared metamaterials to selectively absorb or filter certain wavelengths, it will have an impact in the thermal management inside a building or the building envelopes. So why not? But always, when you're trying to apply a new technology for a building sector, there are always a challenge with cost. And is it going to address the new buildings, which is relatively straightforward? But if you can make it even retrofitable for existing and old buildings without affecting the building aesthetics, and also at affordable price, I think that will be a true solution. But yeah, the short answer is yeah, why not? Great idea.
Thank you, Phil. And there is a question for Dave. Your talk focused primarily on aviation. How different or not is the maritime fuels challenge?
It is similar in many ways, but slightly different. Certainly the scale of the maritime problem is very similar to aviation. It's probably a couple % of worldwide CO2 emissions. Certainly contrails are not a problem in the maritime industries. As well, certainly for long distance transportation, energy density is always important, but both volumetric and mass specific energy density are probably slightly less important in the maritime industry, which makes less energy dense fuels potentially a little bit more attractive than they would be in the aviation industry. So things like ammonia, liquefied natural gas, perhaps even ethanol may be a little bit more attractive in the maritime industry than they would be in the aviation industry, where energy specific or for specific energy is absolutely critical for the performance of aircraft.
Thank you, Dave. There is a question for Emily. In terms of land requirements, how does nanocellulose compare to traditional feedstocks like corn store?
Yeah, thank you for that question. Nanocellulose is actually a byproduct of the pulp and paper industry. So if you can get a sense for how big those requirements are. To be honest, though, I haven't quite figured out the conversion from land to ton of bioplastic or nanocellulose to figure out that equivalent. But what I will say is with the nanocellulose industry, I believe we're at about 1,000 tons per year production, if that, globally right now, and that's comparing to about 380 megatons of the plastics industry. And also, as a side note, the cost for nanocellulose is about $50 to $100 per kilogram, whereas plastics is closer to like $1 per kilogram. So the industry has a long way to go, even to catch up to the volumes that we're talking about when we're talking about plastics, as well as the price point that plastics offer.
Thank you, Emily. And I can take the next one. Do you think it is possible to change the hierarchical control as exists today to something for the whole grid? That's a very important question. So obviously we cannot say that we have a new control system for the power grid and then stop the power grid, for a couple of weeks, because of a couple of months, because we are changing that. So it's actually very critical to find a solution that is a better control strategy, a better control system, but somehow is able to live with the existing solution at the same time. And then we can actually, change the control system to a new one, but allowing the old one to be, living with the new one at the same time. So this is a huge problem, a huge challenge, but I think this is the only way, to actually improve, the control system to allow, all the things that are coming, because we need, a new control system eventually, but we have to continue, the operation of the grid, so this, two solutions living together is part of the solution. Thank you for the question. And I have another one here for Bob. Do you know if there is a potential gain in the energy intensity per computation going from classical to quantum?
That's a fantastic question. I hear that one a lot. And the answer is, if we judiciously use quantum computers. Because I know everybody's afraid, they see the big cryostats for 50 little qubits. But the way to look at it is this. If you're truly exponentially decreasing the complexity of the problem, the time it takes to solve it, 2 to the 300 is more than all the atoms in the universe. So for problems in which you fully utilize quantum computers, you are taking problems that literally no amount of energy could solve and making them soluble. So don't worry about them being big, power-hungry servers yet. Let's direct their use to the cases in which they make a tremendous gain in energy. Hope that answers the question. Good question.
Sure. Thank you, Bob. And there is another one for Phil. How does ARPA-E think about different requirements with different priorities in different climate zones?
I think it's a good question. Let's take a step back and look at the general trend. We are trying to decarbonize a lot of things by electrifying a lot of things and switching the fuel to make the electricity to renewable electricity. And doing so will basically increase the electricity demand. They will create a lot of peaks over different time and different season. And with that change, one thing that is arising as a problem, but not getting a lot of attention, is the winter peaking problem. We already see the summer peak problem, and our grid and T&D structure has to handle. But we're going to see even more peaks in the winter, especially when we electrify the heating part of it in the building. So I think anything that could help or operate in a cold climate zone should get the priority. So if you think about adaptive envelopes, if we can retain the heat after absorbing it during the day and keep it in the building so that we can minimize the morning peak in the winter time, I think that would be really ideal.
Thank you, Phil. And I can take the next one. In addition to individual microgrids, do you see microgrid clusters as assets for oscillation damping? Of course, yes. And actually, I think that the idea of microgrids, what we have, behind the microgrids is resilience of the power grid, reliability of the power grid. So, because instead of having just one system, just working together, but just one system, we have many individual systems that are working in a concurrent way, with coordination. But the problem is that many times we design microgrids with different objectives. So, and then we have different control systems because we are looking for, different targets, economical or resilience or other things, right? So we have then, as I mentioned, previously, we need, a control system that is able, to coordinate all the clusters of microgrids in order to improve the resilience of the power grid. But this can be a solution, to have a very, very resilient, power grid at some point. So, so the answer is yes. Question for Dave. Has the mitigation of contrail formation and the associated warming impact been a focus of ARPA-E aviation efforts thus far?
The shorter answer is no, it hasn't. Our focus has principally been CO2. I guess another question is, should it be? And the answer is probably yes, although the error bars on the impact of contrail formation are certainly very, very significant. But certainly the midpoint of that range suggests that contrail formation is actually more important than CO2. And if that's the case, then actually just shifting to hydrogen and emitting water vapor, just like we emit CO2 and water today, is not necessarily going to be beneficial for the environment. So we need to look at the fuel very carefully, and then how we emit the products associated with the combustion or whatever reaction we use to generate the thrust power that we need on the aircraft. We need to look both carefully at the fuel and the emission process.
Thank you, Dave. Another question for Bob. Crypto mining has become a major energy consumer. Can quantum computing make it more energy efficient?
Oh, well, my simple answer, I don't know the exact answer to that one. I'm sure a lot of people are working on that one. But I would point out just two things on that. One is the first quantum algorithm that actually showed its a great advantage over computing was the Shor's algorithm, which is for factoring. So there's many different ways of doing cryptocurrency. My guess would be yes, it could make an impact. But I'll turn that question around. A beauty about, I've been talking about quantum computation, but quantum communication has the virtue that basically it can't be hacked, and if it is, you know it's there. So maybe all those secure transactions could have a much lower energy load by securing the transaction by a completely transformative way of ensuring integrity. So maybe someone out there will know how to solve that. Thank you for that question.
Thank you, Bob. I think we have time for maybe two more questions. There is one for Phil here. Are you limiting your possible solutions to the building envelopes only, or new ideas for equipment and other aspects are welcome as well?
I think this is a big problem, so that we need to really take all hands on deck approach. So envelope, improve the energy efficiency of the envelope is one way, but we also need to look at other ways to improve and downsize the HVAC equipment by making them better. And also another aspect we need to consider is how can we make the buildings more energy flexible? So we have traditional demand response program, or we can utilize the DERs, but there are other ways to provide building energy flexibility. And I think one way to do that is distributed energy storage systems, such as chemical batteries and thermal energy storage systems. Everything's interesting.
Thank you, Phil. And I can take the next one. What scale should grid oscillation control architecture be implemented? By microgrid, by balancing authority, by state? That's a good question. You know, let's say that we have here two problems. One is the voltage problem, and the other one is the frequency problem. So to damp the voltage oscillations, this is definitely a local problem. So you have to implement control systems locally. For the frequency, this is a very large, you know, in terms of, I mean, can be states or even, you know, across states, you know. So, and again, what we need is to develop a control architecture that can, or, you know, allow, you know, many generators working together in order to control frequency. So that's the answer. You know, it depends, frequency or voltage, but definitely for frequency, that should be a very big, you know, solution, you know, allowing, you know, hundreds or thousands of generators, you know, to work with frequency. And I think this is the time we have for today. I see, you know, many more questions here in the chat, and I am sure that we have probably many more. So feel free, you know, to email us, you know, and we'll be very happy, you know, continuing the discussion, you know, after this. And thank you very much, everyone, for attending this last fast pitch of the summit. Thank you very much. Bye.
Thank you.